All right, I know I've been giving you a lot of homework problems here. I think once we get done with chapter 4, there will be fewer completion problems, at least. I think what I'm going to do is I'll probably make a key for maybe just as many problems as chapters 2, 3, and 4, but I won't assign all of them. You'll get to pick a certain number each completion assignment. So that will cut down. But I think getting through chapter 4 as far as doing a lot of calculation related questions actually is pretty important if we're going to really get the material. So once we get to chapter 5, I think we'll cut down on the total number of completion problems. Plan for today. Last time we looked at why does addition mod n work. This time we're going to look at why does multiplication mod n work, so to speak. You know, why can you always mod wherever you want to, essentially, is what I mean there. Related to that, why do elements in UN have inverses in UN? Let's see if we can figure that out. And look at an interesting matrix group and talk more about subgroups. Then lecture 7b, we're really going to focus heavily on cyclic groups. What makes a group cyclic versus not cyclic? Think about some questions related to cyclic groups and try to answer them, especially on Friday. I think what we're going to do is we're going to take an approach different than the book does in chapter 4. The book proves lots of things in chapter 4, which you should certainly study and know how to prove. We'll probably talk about those some next week. But on Friday, I think we'll just sort of take a real sort of empirical approach to studying cyclic groups. We'll look at a lot of examples, and we'll try to see what is common to all these examples. What kinds of, can we answer these questions is what I'm getting after by doing experiments, so to speak. Okay? So why does multiplication work? And I think there's no typos today here. This really is meant to be multiplication here today. Why does multiplication mod n work? Well, actually, exercise 7 comes into play just like it did on Monday with addition mod n. It's still really important to realize that two numbers, a and b, two integers, are going to have the same remainder when you divide by n. When you mod by n, they're going to have the same remainder if and only if n divides a minus b. Okay, that's still going to be helpful to realize. And then there's, actually, this is the other part of exercise 9 that I did not write. There's this fact: if a mod n is a prime and b mod n is b prime, then we can look at the product ab mod n. It's the same as the product of a prime and b prime mod n. And again, using the function notation, you can write it like this. Why does that work? Well, it's again using exercise 7. And again, I'm doing these things partially because it's important to do, I think, to really understand what's going on with modular arithmetic, but also because these kinds of proofs could show up on exam 1. So taking a look at number 9, let's go ahead and prove that. Suppose a mod n equals a prime and b mod n equals b prime. I want to show that ab mod n is a prime b prime mod n. In other words, when you divide ab by n and a prime times b prime by n, you get the same remainder. Use number 7. That's the easiest thing to use. But we do need to still use the division algorithm. We still need an equation that we can manipulate. We already have the remainders, a prime and b prime, that we get when we divide by n, that come from the division algorithm, that are definitely between 0 and n, possibly equal to 0 and less than n. But we can say also that there exists, say, q1 and q2, such that a equals nq1 plus a prime, and b equals nq2 plus b prime. We already are given a prime and b prime to be the remainders, and they're also, again, assumed to satisfy this. That's the implicit assumption here. Again, come back to what you want to show. AB mod n is A prime B prime mod n. In other words, use exercise 7, show n divides the difference. This minus that. Just looking at it that way, maybe makes you feel a little nervous. How in the world am I going to show n divides that? Well, okay, yes, use these equations. It may not be clear that it's going to work, but if you're doing something on scratch paper at least, which I think you should always do when you're figuring out proofs for the first time, you just try it and see if it works. Replace A with nq1 plus A prime. Replace B with nq2 plus B prime. Don't forget to subtract A prime times B prime. Do your algebra, see if it simplifies in such a way that you can see divisible by n. And it will be because the A prime times B prime that you get after foiling this will cancel. You will get an n squared q1, q2. The n squared is no problem. That's still divisible by n. nq1 b prime plus nq2 a prime plus a prime times b prime. Don't forget to subtract the a prime times b prime. Those now cancel. And you're left with something for which you can factor out an n. And that shows, therefore, n divides the difference AB minus A prime B prime. Therefore, AB mod n equals A prime B prime mod n by the result from exercise 7. Okay. Which you may use on the exam. You may use exercise 7. You don't have to remember that it's exercise 7 from chapter 0. You don't have to remember that. But this is a fact you should store away in your mind. You should remember this for the exam. I think we've worked with this enough that you probably can remember it pretty quickly. Remember the fact from exercise 7. All right. But what about UN? Remember what UN is called? It's called the group of units modulo n. You might wonder why they're called units. We won't really see why they're called units until a month and a half from now, chapter 12 or 13, I think. Why is it a group? What is the UN? It's as a set, it's the set of all positive integers less than n that are relatively prime to n, which always includes 1, so the identity is always in there. Does it satisfy closure? Well, we're not going to answer that today. But we can at least try to understand why every element in UN has a multiplicative inverse in UN, right? It's multiplication mod n, that's the operation in UN, not addition. And it's this problem, which was a completion problem, that essentially is the reason why every element of UN has a multiplicative inverse. Why? Because if you've got, a fixed n, and you've got a number a, let's say is between 0 and n, this equation, ax mod n equals 1, has a solution for x, a value for x to make that true, if and only if d is 1, where d is the GCD of a and n. Now, if d is, a number a between 0 and n, greater than or equal to 1, I should say, a positive integer less than n, is going to be in UN if and only if this GCD is 1, right? It's got to be relatively prime to n. That's what elements of UN have to satisfy. And it's exactly in that situation when the GCD is 1, when these are relatively prime, that you got a multiplicative inverse, a number x satisfying this product equaling 1 mod n. And you can take that number to be between 0 and n, to be in un. I guess that doesn't fully verify that x itself is in un, but it will be. Let's just show the if and only if part of this one here. So this is chapter 0, number 11. It's an if and only if. Let's do both directions. This is also of a level of difficulty that could show up on exam 1. Suppose there exists an x, it's an integer. We won't worry about it being between 0 and n because it's not part of the problem, but you could take it to be between 0 and n, it turns out, such that ax mod n equals 1. The goal is to show that the GCD of a and n d is 1. That sounds like it could be difficult. But always remember, the GCD as a linear combination theorem is really useful. If you've got your book, look at it again. It's on page 4. Let me put it over on the side here. It says two things, and they're actually both important. Given two integers, a and b, there exists s and t integers such that the GCD of a and b is as plus bt, a linear combination of a and b. Moreover, this is important too, GCD of a and b is the smallest positive integer of this form, and by this form we mean as a linear combination. So, this is really important to realize. You can show that the GCD of two numbers is 1 by finding a linear combination of those two numbers that equals 1, because 1 is the smallest positive integer. And the GCD is the smallest positive integer of that form. Say that again. Listen real carefully. If, given your two numbers, you can find a linear combination that does equal 1, since 1 is the smallest positive integer, and since the GCD is the smallest positive integer of that form, if it equals 1, 1 must be the GCD. Those numbers must be relatively prime. So that's really the main thing you're after here to show this, is you want to find a linear combination of a and n that equals 1. And then you can really apply the second sentence of the GCD as a linear combination theorem. All that is now is just a matter of teasing out what this means. Again, the division algorithm now implies then that there exists a quotient Q such that when you divide a times x by n, you get q times n plus the remainder, and the remainder is going to be 1. Because you're assuming this is true. And we're almost there now, because now just rearrange this to get 1 on one side by itself. We're trying to show that the GCD of a and n is 1. Write it like that. That's a linear combination of a and n. It equals 1. 1 is the smallest positive integer, and also GCD of a and n would be the smallest positive integer of this form. We've got something in this form equaling 1. The GCD of a and n must be 1. That's what we're calling D here. And that does it. You should say, by the GCD's linear combination theorem. And again, I'm writing implications to save some time. You should write sentences, as usual. How about the other direction? Just take the steps in reverse. If D is 1, if this GCD is 1, then by the first sentence of the GCD is the linear combination theorem. There exists integers where this kind of equation is true. Suppose D equals the GCD of a and n is 1, then there exists integers, we can call them s and t now. S and t such that as plus nt equals 1. Now rewrite that as as, maybe I should have called it an x instead of an s, but that's okay. As equals n times negative t plus 1. Now remember, Q and R for the division algorithm are unique with respect to the fact that R, the remainder, is between 0 and the thing you're dividing by, in this case, n. The quotient, Q, could be negative. We don't know really whether t and s are negative or positive here. So negative t could be negative or positive. But it doesn't matter. All that matters is the remainder there is between 0 and n. N is taken to be positive, I guess. This is in the form of the division algorithm. This must be the unique remainder guaranteed to exist from the division algorithm. So that means that AX mod n has a solution. Equals 1 has a solution. And that solution would be x equals s, whatever s happens to be. Doesn't verify fully that s, when you at least mod it by n, is in un, but it's part of the way there. There is a solution to this equation. Okay. So again, this is the type of level of difficulty for a proof that could come up on the test. Here's an interesting type of general linear group. Allow the entries of the matrices to be of the forms, or to be from ZP where P is prime. Okay, so GL stands for general linear. It's just special notation for a set of square matrices. In this case, 2 by 2 matrices, and we will keep our examples to 2 by 2, but of course you could do 3 by 3 or 4 by 4 or 5 by 5. ZP, the coefficients, the entries of the matrix, are in ZP, where P does need to be prime here. A, B, C, and D are in ZP, and again, the determinant must be non-zero. The assumption here is all these operations that are going on, both when you multiply the matrices, which does mean you'll need to both do multiplications and additions, and in this multiplication, these multiplications and this subtraction, you're assuming these operations are done modulo P. Okay? Turns out such matrices have inverses. The determinant being non-zero guarantees that. And again, the operation is matrix multiplication. And this is a group. Can you find the inverse matrix of a given element? Yep. And you can use this formula, which you should have seen in the reading. Now this formula works even if A, B, C, and D were, say, real numbers, or even complex numbers. This formula works in general, though you don't put the modulo P there. If you were dealing with real numbers or complex numbers, you know, this thing to the -1 is really the reciprocal of the determinant of the matrix. Here you don't write it as a fraction, though, because we're dealing with ZP. You write it as the inverse of the element AD minus BC. That would be in ZP. Doing everything modulo P. So I think you had a completion problem like this. Let's just take an example. Let's consider GL2, say Z3. And I might wonder, what is the multiplicative inverse of the following matrix? I better make it invertible. Better make its determinant non-zero mod 3. So I do need to be a little careful. Oh, let's say I do 2, 1, 1, 1. So that's a matrix in ZP. And the determinant will be 2 minus 1 is 1. Mod 3 is still 1. It's non-zero. And if I use that formula for the inverse, I can write it like this. This inverse, by the way, is the inverse with respect really to UP. Multiplication, a multiplicative inverse. You switch around the main diagonal elements, the A and D get switched around, and you negate the off-diagonal elements. Mod 3. And simplify. Mod 3 means the -1 gets replaced by 2. You can write it this way. And what is the multiplicative inverse of 1 mod 3? It's itself. Didn't have to be. Yeah. If it were a multiplicative inverse of 2 mod 3, that would also be itself, mod 3. Right, because 2 times 2 would be 4, which would be 1 mod 3. 1 is the multiplicative identity mod 3 in U3, so the inverse, multiplicative inverse of 1 is going to be 1. So it simplifies to that. And you should be able to check it. How? You should be able to multiply these matrices mod 3 and see that you get the identity matrix. 2 times 1 is 2, plus another 1 times 2 is 2 plus 2. Ultimately, everything's mod 3 again. But I'll write it like this first. Then we have 2 plus another 2 there as well. Wait, did I do that right? Yes, 2 plus 2. 4 plus 2 for the other one. Next one there. 1 plus 2. And then finally 2 plus 2. Mod 3. 4 mod 3 is 1. 6 mod 3 is 0. 3 mod 3 is 0. 4 mod 3 is 1. We do get the identity matrix. And you can check it the other direction as well. Careful, again, some matrices could look invertible, but not be, like that matrix. That would be invertible if you're dealing with your usual matrix operations, but we're doing matrix operations mod 3. The determinant of this is 4 minus 1 is 3 is 0 mod 3. That's not invertible. It's actually not even an element then of this group. This group right here, because it's not invertible. when you write these things, you should technically always be writing the mod 3 to remind yourself and to remind the reader that you're doing these mod 3. These are finite groups as well, by the way. I mean, if you only allowed yourself to, well, consider all matrices whose entries are from Z3, 0, 1, and 2, and didn't worry about whether the determinant was 0 or not, didn't worry about whether they were invertible or not, you'd have 3 choices for each entry. And so the total number of entries would be 3 to the 4th, which would be 81. Not all of those are invertible, but it does put an upper bound on how big GL2 of Z3 is. It's got to have less than 81 elements. It's a finite group. Okay, and there are some pretty interesting groups. Can I clarify anything? Please stop me if you're feeling confused. You know, people don't typically do that, but I want you to feel comfortable asking a question. So we looked at some examples of subgroups last time. I will re-emphasize those same examples, especially this very first one. This is the most important kind of subgroup there is, in general. You got an arbitrary group, could be a finite group, could be an infinite group, could be cyclic, could be not cyclic. Talked about what cyclic was last time. I will remind you again today. Then the set of, you got an element, A. The set of all integer powers of A is a subgroup of G, called the cyclic subgroup generated by A. Okay? Very most important kind of subgroup of any group to consider. We verified it was a subgroup with the one-step subgroup test last time, and you should be able to do that on the exam. That would be another exam level proof that you should be able to do for the exam. Notationally, again, you see in our book the pointy brackets. I will remind you one more time that other books use parentheses. Some books use pointy brackets. Some books use parentheses. It's analogous to the span of one vector. In a vector space, it's analogous to a one-dimensional subspace of a vector space. It's not exactly the same idea, it's just an analogy. So one vector spanning the subspace, you've got one element generating the subgroup. Use the terminology that we have here. Spanning in linear algebra, generating here in group theory. Don't mix up the terminology. We also looked at the idea of the center of any group. G is an arbitrary group, could be abelian, could be non-abelian. The center is the set of all things in G that commute with everything else in G. And the center could just be the identity element. That would be a very non-abelian group, you might say. Or it could be the other extreme, it could be the entire group. That's going to happen if and only if the group is abelian. Usually, for a general non-abelian group, it's going to be somewhere in between. It's going to be some, perhaps, non-trivial subgroup. We verified this was a subgroup with the two-step subgroup test last time. That's also a proof level you should be able to do on the exam. The next slide, which I won't go to yet since some people are still writing here, involves something called a centralizer of an element. Denoted by C of A. This is called the centralizer of the element A. It's the set of all things in the group that commutes with A, with this given element A. Set of all little g and capital G, say, such that the product of G times A equals A times G. Certainly, this is or maybe I should say clearly, clearly, the center of a group is a subset of the centralizer of any element. And in fact, the centralizer is going to be a subgroup of the group. For any element A, this will be true. I haven't proved that. But that is true. And clearly, the center is a subgroup of any centralizer because, think about it, since they're both, if you verify that they're both subgroups of G, you would only have to verify that this is a subset of that. Did you catch what I just said there? If you've already verified that both the center and the centralizer of the given element are subgroups of G, to show this, you really only need to show the set inclusion. This is a subset of that. Because they're already subgroups. Got an element that commutes with everything in G, it's going to commute with A. Done. Right? That is clear. C of G is the set of everything that commutes with, set of everything that commutes with everything else in G. So if you've got an element that commutes with everything in G, it's also going to commute with A. Because A is a part of G. This is true no matter what A is. And you can say a little bit more. You can say, in fact, that the center equals the intersection of all the centralizers. Since it's a subgroup of every centralizer, you definitely have it being a subgroup of the intersection, though I haven't yet proved that the intersection of a bunch of subgroups is also a subgroup. That is true. I think we'll do that after the quiz here in a few minutes. Say it again. Listen carefully. It does turn out to be true, again, that the centralizer of any element is a subgroup of the given group. It also turns out that an intersection of any collection of subgroups is also a subgroup, so this is true. And because ZG is a subgroup of every centralizer, it's also going to be a subgroup of the intersection of all the centralizers. Got an element in ZG. Write ZG there. What does it mean to be in the intersection there? It means to be in everything that's being intersected. And that's what I just said there. Does it go the other direction? I claim it does. The intersection of all the centralizers should also be a subgroup of the center. Think about it. What does it mean to be the intersection? It means you're in everything that's being intersected. You're in all the CAs for every A. To be in a given CA means you commute with A. So if you're in all the CAs, as A varies over G, you commute with everything in G. You're in the center. Therefore, these two things combine to say these sets are equal. These subgroups are equal. Which is a useful thing to know. Okay. We'll continue after the quiz.